Is there life elsewhere in the universe? Anyone who has pondered the immensity of the cosmos has probably wondered at some time or another whether life exists beyond our planet.
One of the most interesting and exciting questions that people have been asking for millennia is, are we alone? You know, even as a child, I stared up at the night sky, saw all those stars, and couldn't imagine that some of them didn't have planets with people on them who were looking back at me, wondering the same thing. We are now at the point where we can scientifically answer that question.
The search for life beyond Earth has been buoyed by recent discoveries made by NASA's Kepler telescope. It's looking for planets outside our solar system known as exoplanets. Kepler measures the brightness of distant stars and tracks a star's dimming when a planet passes in front. Up until 1995, exoplanets were purely theoretical, but scientists have since identified thousands of them.
Just 20 years ago, we didn't know of any planets beyond our solar system. And now here we are, we know that there's pretty much a planet for every star. And then we know about 1 out of every 5 of those planets could harbor life. That's such a profound difference in one generation's worth of work in our understanding of the cosmos. It blows me away every time I think about it. And it blows me away every time I go out at night, because I can literally go and not just count stars, I can now count planets.
But one thing that has been very important, and is one of the real growth points of astronomy at the moment, is the realization that most stars are orbited by retinues of planets, just as the Sun is orbited by the Earth and the other familiar planets, and that many of those planets are rather like the young Earth. There are probably within our Milky Way galaxy billions of planets rather like the Earth. And of course, many people would guess that there is life on them, but we can't be so sure about that, nor what life is like.
In July, NASA scientists announced the discovery of one of their most exciting exoplanets yet, Kepler 452b. Located some 14,000 light-years away, the planet is in the habitable zone, which means it's the right distance from its own sun and also the right size to potentially be Earth-like.
So Kepler 452b is one of the most habitable planets, or one of the most potentially habitable planets that we've ever found. Of the things that we're able to measure about this planet, there's a lot of it that seems much like what we experience here on our own home planet. And that's what's got a lot of the scientific community so excited.
There is a limit to how much we can learn about Kepler 452b because of its distance. NASA is launching the James Webb Telescope in 2018 to find Earth-like planets closer to home, so they can study their atmospheres for biosignatures that would indicate the presence of life. But there's another way to learn more about distant planets beyond what the Kepler telescope can tell us, and that is to look for signs of intelligent life. Frank Drake has been listening out for signals of intelligent life elsewhere in the universe for over 50 years. Mr. Drake came up with something called the Drake equation, which is a mathematical formula that estimates how many advanced civilizations capable of transmitting signals might exist in the universe. He co-founded the SETI Institute, the search for extraterrestrial intelligence. Scientists at the SETI Institute have been searching for intelligent life for the past few decades.
How does SETI search? Well, we look at our own technology and determine which one of our technologies is detectable across the distances which separate the stars. What we can detect is our radio signals, our television broadcasts, of which of course there are thousands, our radar transmissions, which are even easier to detect. And so we search for those. And so just recently to the radio search, we have added a light search.
SETI researchers have not come across any signals yet, but they say this is to be expected.
So in our galaxy, a couple of 100 billion stars. We've looked carefully at maybe a couple of thousand stars, right? That means we've looked at 1/1,000,000th of the star systems in our galaxy carefully, 1/1,000,000th. So, that's like going to the ocean, taking a glass of water and saying, you see any sharks in there, Bob? Well, I don't. Well, I guess there are no sharks in the ocean. Well, that'd be a little premature, right? All it means is your sample size isn't big enough. And that would be very discouraging if it weren't for the fact that the technology keeps getting faster. So there's hope.
SETI's efforts recently got a huge boost with the launch of Breakthrough Listen, overseen by Martin Rees, Stephen Hawking, and Frank Drake, and funded by Silicon Valley entrepreneur Yuri Milner. The project will greatly expand the organization's capacity to search and sift through data. But scientists aren't only interested in discovering life forms light years away.
Of course, the only places we can directly look for life apart from Earth are on the planets and moons of our solar system. And there has been talk about, could there be some kind of life on Mars? Could there be something on comets? Could there be something under the frozen ice on Europa, one of Jupiter's moons, or Enceladus, one of Saturn's moons? And it's possible that people will find life. No one expects any very complex life in those places, but even evidence of simple life would be important.
At first glance, our solar system seems like a rather unlikely place to find life beyond Earth. But the reason scientists think it is plausible is because of the discovery of a group of organisms called extremophiles that live on Earth.
So extremophiles are a group of organisms that we've discovered that live in what we consider extreme environments. And so we have found organisms that live at temperatures that exceed boiling water, at pHs the same, lower than battery acid.
Scientists are looking at the moons of Jupiter and Saturn, as well as our nearest neighbor, Mars.
And so what we're looking for is something that might, with a microscope, might look like life. Life needs water, so we've been very interested in water worlds. So what the Curiosity rover is doing now is going around Gale Crater and investigating ancient riverbeds and features that indicate, and chemistry that indicate that there was water present.
You know, you look at Jupiter, it's a big gas ball. You figure there's probably no life there, and that's probably true. But Jupiter has, I don't think, like close to 70 moons that we know about. And several of them are very large, you know, the size of our own moon, maybe even a little bit bigger. At least 3 of them are thought to have underneath their surfaces, and the surface might just be ice or rock, but underneath, maybe 10 miles down, maybe 100 miles down, they might have liquid oceans, hidden, dark, inky dark oceans down there with liquid water that's been sitting there for 4 billion years. So after that length of time, there might be something that's cooked up in there.
The hope is that if we find further life in our solar system, on places like Mars, we will improve our understanding of how easily it might have started elsewhere. But there is another way to answer this question, determining how it started on Earth.
So until we understand how life began, we don't know how likely it is or how unique the pathway was that led to life on Earth.
One man who is trying to come up with an answer to this question is Jack Szostak. In his lab at Harvard University, he's trying to determine how easy it is to create life by making it himself.
So we work on the origin of life. We are trying to do simple experiments in the lab that will give us some clues as to how life got started on the early Earth. Our approach is to work with the chemicals that we think were involved and try to see how they could assemble into a simple kind of cell.
Modern cells are intricate nanoscale factories stuffed with thousands of different chemicals, each taking part in a complicated and messy web of reactions. Long strands of DNA encode a cell's genetic information. Shorter strands of RNA carry that information around the cell, telling it how to manufacture the proteins that run the chemical reactions it requires to live. It seems unlikely that these systems all evolved at the same time. At the Szostak lab, they're focused on 2 experiments. One to work out how primitive cell membranes could grow and divide into daughter cells, and the other on RNA replication.
So we hope to be able to recreate the conditions in lab that allowed life to come about in the first place on the early Earth. And a big part of that is learning how to make RNA that can undergo spontaneous self-replication without the need for modern-day enzymes.
Dr. Szostak and his team have already created a protocell from a blob of lipids which contains RNA. The sticking point at the moment is working out how to make RNA that can copy itself without relying on a helping hand from RNA enzymes.
The ultimate goal of this is to create, from chemicals, a simple living system where we can see Darwinian evolution operating, the emergence of new functions. So in a sense, it would be a reconstitution of the beginnings of biology in a lab setting. One of the things we hope to learn from that, of course, is how life might have started on the early Earth.
If it is a difficult process, reliant upon various bits of luck or circumstance, then it is possible that we are a cosmic fluke, one that isn't going to be repeated elsewhere. But if experiments like Dr. Shostak's show that life emerges easily, then the odds of life appearing elsewhere in the universe look more likely. Perhaps one day, when we're looking into the night sky, we'll finally know the answer to the question, are we alone?